the 2D convolution using the equation method. The question is the same which we have done in the previous class for y of 0, 0 and y of 2, 0. Today you need to determine y or h of 2, 2. I is given to you here as 1, 2, 3, 4, 5, 6, 7, 8 and 9, and f is also given here. Can you try to find out y of 2, 2? Y of 2, 2. If you have noted I and f, can I go on to the equation?
Yes.
Ma'am, 41 answer.
Yeah, no problem. I'll take it. I'll take this data.
Answer 41, ma'am.
This is your data. 1, 2, 3, 4, 5, 6, 7, 8 and 9.
Ma'am?
Yes,
Ma'am, is y of 2, 2 equal to 2, ma'am?
I'll come to the equation. That's why if you have seen I and f, can I go on to the equation? You recall your equation was y of mn, I equal to minus infinity to plus infinity, j equal to minus infinity to plus infinity, I of ij, f of m minus I, n minus j. So your expression, what I have asked you now is y of 2, 2. You would recall in our previous discussion, we had considered that the summation from minus infinity to plus infinity will become a finite value. It will extend one value above 2 and one value below 2. So below 2 it will be 1, above 2 it will be 3. So your values will be 1, 1 and 3, 3. With this, you will have to form different combinations. For example, I think the format we have used is I of 1, 1, I of 2, 1, I of 3, 1, in whichever manner you want, and the corresponding f. I of 1, 1, 2, 2 and 3, 3. Can I go on to the next step?
Yes, ma'am.
Expansion is I of 1, 1, I of 2, 1, I of 1, 1, I of 2, 1, I of 3, 1. You will be repeating it for I of 1, 2, 2, 2, 3, 2, and again for 1, 3, 2, 3 and 33. First, try to fill in the I values so that you are stuck with it. Or if you feel you are comfortable completing one row, you may do as you please. Each person has a specific way of doing things, so you may follow your convenient way. I have followed a method wherein I would like to prefer finishing all I's and then going for F's. Or F can be written then and there. It is I 1 1, so F 2 minus 1, that is 1. 2 minus 1 is again 1, so F of 1 1. The next one is 2 minus 2, it is 0. 2 minus 1 is 0, so it is 0 1. And next case is 2 minus 3, it is minus 1. 2 minus 1, it is 1. Similarly, you may write the F's for the next two rows also. Just see whether you are getting the same values. Have you finished this case? Can we move on? Check whether you have got f of 1 0. I think I told you. As a check, I of 2 2 will have f of 0 0. If you have got that, it is correct. That doesn't mean that here you could make mistakes. For example, you could write it as minus 1 instead of minus 1 0. Anyway, this term will not affect because this will be later removed in our expression. Only valid values of I will be retained, which means coefficients of I with 0, 1 and 2 alone will be retained. Is it over this stage? Can we go on to the next stage? Anybody still struggling with this stage? Have you completed it? Yes?
Yes, ma'am.
Yes. Shall we move on to the next one? Most of you have completed.
Yes, ma'am. Yes, ma'am.
Bansi, have you finished? Are you there? I don't know whether he's present. Yes, Bansi, have you finished? Govind, finished? Shall we take the next one? Yes or no? Or you want me to explain this again?
Yes, ma'am.
You want me to explain it again?
No, ma'am, it's finished.
You finished?
You can go to the next slide.
Yeah, I'll move on to the next slide. So the next slide tells us that we have in many places f with 0, 1, 1, 1, 1, 0, 0, 0, which are all feasible values, but you also have minus 1, 1, minus 1, minus 1, etc. So in order to consider the flipping both in the vertical axis and in the horizontal axis, we have carried out a shift by 1 in both the horizontal axis and the vertical axis. I mentioned that 0 becomes minus 1, 1 becomes 0, and 2 becomes 1. The same thing, we are just changing it, but please note there is no change in the value of f, unlike the graphical case where we were flipping it. With these values, you need to now substitute it. Okay, can you try the substitution? The next step is you will cancel values which do not have 0, 1 and 2 in I, which means this term will go, this term will go, this term will go, last full row will go, and last full column will also go. This means this 3 and this 3 will go, only these 4 will be remaining. Is it correct? So this is what you might have got. Next stage is we would be cancelling all this, and then we are just substituting I of 1, 1, f of 1, 1, I of 2, 1, I of 1, 2, I of 2, 2, and the corresponding f values. Just see whether you're getting the same values. Have you got this answer? Can we move? Yes or no?
Yes, ma'am.
Yes, yes, ma'am.
I hope you have started understanding and applying things. So with this base, we will go on to understanding the basics of spatial filter. A small portion is there which we have not discussed, which is called as the neighborhood pixel operation, both in the adjacent way and in the connected way. We will consider it just before segmentation. So in order to do that, now we will just understand what is a filter, how the filter works. I will just complete that, and I would like to have a 10 minutes discussion with you. Is it okay? We are going to consider filters. Most of you are aware we have used filters in signal processing, in analog electronics, in other applications you might have implemented filters. Even for your BTech projects you might have implemented filters. I'm just quickly going through the 4 basic types of filters. This is actually called as their ideal response. The first one is the low pass filter. As the term suggests, it allows low frequencies to pass through. What is the meaning of this low frequencies to pass through is, suppose I have a signal which has, if you recall our one sampling example, where we had a 50 Hz signal, we had a 150 Hz signal, we also had a 250 Hz signal. Suppose I want to retain only the 50 Hz signal, then naturally I should use some device which will allow only signals up to 50 Hz to be there and remove all the higher frequencies. This removal of higher frequencies is what has been shown here as, I would call it as, this is usually called as the brick wall response of a filter, perhaps you remember it, wherein we assume that the magnitude of the filter is 1, is it right, which could be naturally changed depending upon the application, but in an ideal case of a filter will have a magnitude of 1 and it will have a response such that it will allow all frequencies up to that cutoff frequency which you are choosing to pass through. When we say what is the cutoff frequency, as I mentioned, I am going to choose it as 50 Hz. If I choose it as 50 Hz, all frequencies up to 50 Hz will be allowed. Frequencies greater than 50 Hz will be not allowed to pass through, or they will be removed. This is what is the meaning of low pass. What is high pass? High pass is just the reverse of low pass. Is it right? If you see the function or if you see the diagram, you can see that is what it is. This tells us the amplitude of the response or the magnitude of the response, and this tells about the frequency. So basically it is the frequency response of a filter, and since it is the frequency response of a filter, what we are going to have is, here we are going to have a cutoff frequency, which means the same example where we have 50 Hz, 150 Hz and 250 Hz. Let me assume I want to remove the 50 Hz and I want to retain the 150 Hz and 250 Hz. Then I can choose a cutoff frequency of 50 Hz. Suppose I want to remove 50 Hz and 150 Hz, then I can choose a cutoff frequency of 150 Hz, so that only frequencies above 150 Hz will be passed, which means 0 to 150 will be removed, which means the 50 Hz and 150 Hz will be removed. Band pass is also a combination, if you see, of low pass and high pass. It has 2 frequencies. One of them is called as the lower cutoff frequency. The other one is called as the higher cutoff frequencies. In some applications, perhaps in notch filter, etc., you will want only certain range of frequencies to be present in your application. When you want only certain range of frequencies, then you will have to choose these frequencies in a suitable manner and allow those frequencies to be present. For example, the same example I go by, where we had a 50 Hz, 150 Hz and a 250 Hz. Suppose I do not want to remove the 50 Hz, nor I want to remove the 250 Hz. I want it somewhere between 100 to 200. Then band pass filter will be my ideal. case, I would choose this between 100 to 150 hertz or 200 hertz, whatever may be the higher cutoff frequency. Is it okay? Band stop, again you would see it is almost, I would say, the reverse of band pass, and maybe you have considered methods how you could construct band pass from low pass and high pass, and also band stop from low pass and high pass. I'm not going into those details, but what is this band stop? In band stop filter, what happens is that you have a lower cutoff frequency called as FCL, you have a higher cutoff frequency called as FCH, which means it is going to allow up to lower cutoff frequency, and it is going to remove frequencies between lower cutoff and higher cutoff. That's where I said it is the inverse of band pass, and from higher cutoff onwards it will allow. Going by the same example of 50 hertz, 150 hertz and 250 hertz, maybe it will have up to 50 hertz it will allow, then it will allow from 250 hertz onwards, which means it will remove the 150 hertz component. This is what is going to be the general basic filter that exists in signal processing, which we call as the basic type of frequency response analysis got from usually the Fourier, but even without Fourier, we can try to understand what is this filter expression, because that's how you analyze it in analog electronics, where you try to analyze it using circuit theory and using the S transforms. So once you have understood what is a filter, our discussion is going to be, we are also going to discuss a filter, and we will call that filter as low pass and high pass. The low pass is going to be a smoothening filter. The high pass is going to be a sharpening filter. So basically, we are going to consider this as the spatial filter. Why should we now introduce filter? We have understood convolution, and from the basics of signal processing, we know that convolution is necessary to understand the filters. So definitely, since we have considered 2D convolution, we are also expecting that we will be having a filtering action with this 2D convolution. That is exactly what we are considering, but what you generally see is, this is what I usually call it as the brick wall response. This is basically the actual response of a expected response. No filter, however well you design, can give this brick wall response. Usually it will have like this. This tapering will be changing, and based on the tapering you will say its characteristic changes, its transition band changes, so on and so forth. Many qualities are adhered to the filter, but basically it just means that you are going to not allow it to just cut off the frequency at 50 hertz. Even before it, it starts slight attenuation, and it even does not cut at 50 hertz. It allows some frequencies beyond 50 hertz also, as can be seen from this graph. You will see that there is actually a change. Even from this particular graph, there is a drastic change in the actual response. What happens in high-pass filters? In high-pass filters also, as you can see, it does not cut the response or attenuate the response exactly at the high frequency which you have chosen as the cutoff. It allows some lower frequencies to pass up to a certain extent, and after that only it does that action. And same thing is true for band pass and for band stop, where you can see that the response does not become equivalent to the brick wall response that we have discussed. It allows some low frequencies to pass through, and same way some more high frequencies than our chosen FCH and FCL. The same thing with band stop. We are allowing only certain frequencies to pass through, but you will see that some more frequencies are getting through. Similarly, here we are cutting it at some high frequency. In our example, we had considered 200 hertz. It may start getting cut at 180 hertz or so. That is what is called as a realistic filter. You might recall that you have constructed, people from the electronics background or even otherwise, you might remember that you have considered the structure of the filters in analog electronics using R, L, C, etc. And it was advised to you that avoid L, because L is actually a bulk element which occupies lot of space while designing. So this is what is basically the realistic filter. And when we discuss about it in the frequency domain, it is the same thing. Only thing is we usually call it as the magnitude response of the filter, and here we use the cutoff frequency and it is given in radians. The response, however, remains the same. And usually here some books also use it as, instead of lower cutoff and higher cutoff, we also use it as passband and band. You will see different terminologies, but basically the filter structure is such that in low pass it allows low frequencies to pass through. In high pass it allows only higher frequencies to pass through, or it removes the lower frequency part. In band pass, as the term says, band, it allows a band to pass through the filter. So that band of frequencies which you allow to pass is given by what you choose as FCL and FCH, or omega A and omega B. Similar is the case for band stop, where you want to stop and where you want to start it to have the frequencies allowed for higher frequencies is going to be called as FCL and FCH, or omega A and omega B as a generic case. This would be the actual filter response, because what you see is, this is what is, I had mentioned it as the transition band. You would see in many cases the transition may come like this, it may come for some more time and then it may go to zero. Please note, it does not settle down to zero. There is a small amount of, you might remember that you had called it as ripple, which will be existing before the filter goes to zero. The same thing is also true for the passband, where you can see that it does not remain at 1. It oscillates between some ripple here called as the passband ripple delta p, and you would recall that it is usually called as 1 plus delta p and 1 minus delta p, because it oscillates between that region, and you will be calling this particular response as what you call as AP, and this region is usually called as passband region and this region is called as stop band. And in addition to the actual cutoff frequency omega C, now you will see two more frequencies are introduced called as omega P and omega S. Omega P is called as the passband frequency and omega S is called as the stop band frequency. So since we have omega P and omega S, how do we relate it to the cutoff frequency? Till now you were talking about cutoff frequency. How did these two terms, omega P and omega S, come in? Omega C is going to be actually the average of omega P plus omega S. You will see that when we consider the actual image processing concept and the signal processing concept. So if you generally see the basics of the spatial filter, it is actually a statement equivalent to the time domain, and you know it's very difficult to do the time domain in the base filtering. So then how can we do it as spatial filter? What is being done here is physically it is meaning that we are going to either preserve the low frequencies as has been defined for low pass, or as in the case of high pass, it will preserve the high frequencies. Band pass, it preserves frequencies within a band, and band reject, it rejects frequencies within a band. So with this base, how can we go on for a spatial filter? Because for a spatial filter, one of the things that is necessary is, one is definitely the image, or what you consider as the signal in signal processing is going to be replaced by an image. In addition to an image, we had just seen in our problems just before when we had discussed for 2D convolution that we had a filter, and I mentioned that that filter is termed by different names like mask, kernel, template or window. Now the question comes, how do I select this mask? We had chosen some random values, 102, 212, something like that, but that is not the manner in which usually the filters coefficients is the term that we use for those values rather than the pixels. So how those coefficients are chosen is basically based on the property that you require what is it that you expect from the filter. And as a result, you will see that this is what I mentioned, that the value, the pixel value in a filter subimage is referred to as coefficients rather than pixels, which is the usual terminology used in most of the images. You know that the values that are written inside that matrix is usually called as pixels, but here you will be calling them as coefficients. So our problem is, how are we going to choose these filters and how these filtering operations are going to be done? That is going to be the basic study that we are going to consider, and this is where I said it is basically that the filtering operation is going to be performed directly on the pixels of an image. So when we do it on the pixels of an image, you might be recalling that when we do it especially towards the top left or bottom left or top right and bottom right, etc., many parts of the filter move out of the domain. So how are we going to consider it? Are we going to add some values? Are we going to pad some zeros? These are some of the issues that we need to discuss when we consider the spatial filters. We will not be discussing too much about those issues. We will come back for that discussion after we complete the operations, which are neighborhood operations, which will be considered just before segmentation. Now the filter will be considered as though an available mask is present and we are just going to filter it with that. As has been mentioned, you will be just moving the filter mask from point to point in an image as we have done in the present case, graphical case, and at each point we will be calculating the response of the filter using the mask or response of the image using the mask.